connections are called synapses. And then somewhere in there you stop losing and you just have sort of a static number of neurons. But nobody has quite figured out, there's new evidence that shows that you do make some more, but nobody quite knows what the trigger is to make more neurons. Nobody knows how it happens. I think it's a hot topic, to say the least, in neuroscience, because if you could figure that out, you might have the solution to a lot of diseases and possibly to some mental capacities, that we wish we had.
Neurogenesis simply means the production of new neurons in the brain. We know that that process continues into at least early toddlerhood, but it had been thought that it stopped again around the age of 2 or 3. And the reason was it wasn't based on empirical observation, it was more just sort of backward reasoning. Namely, the brain is a very complicated computer, and surely if you just sort of haphazardly throw new wires into there, that can't do any good. Therefore, the brain cannot be making new wires, new neurons. Well, it turns out that in an experiment done in the late 90s, which was very clever, they took cancer patients who were terminal and who had, of course, given their consent to the experiment, and they labeled their brain neurons with a particular dye that was incorporated only in dividing cells, in other words, only in cells that were making more of themselves. And this is something that, of course, cancer cells do all the time. After the patients passed away, their brains were examined, and it turns out that a number of neurons in the brain had taken up this dye, and that was prima facie evidence that, in fact, new neurons were being born in the brain. And just to underline, these were elderly people. They were in their 50s and 60s and 70s. So even once you are well past the age of Medicare, your brain is still forming new neurons. And then the question is, under what circumstances does it do so, and can you speed it up? And there the answer turns out to be yes. But surprisingly, you speed it up not by doing crossword puzzles till you're cross-eyed, but instead through physical activity. Something as simple as an hour of aerobic exercise 5 times a week will dial up the rate of production of new neurons in the brain. So there's hope for all of us yet.
Studies have also shown that neurogenesis is amplified by certain mental activity. It takes the right kind of mental activity to achieve positive results. Activities with measurable results that increase in difficulty will challenge your brain to grow and stay healthy.
The brain is constantly adapting to new experiences, learning language at about 1 year, learning other things as they get a little older, learning mathematics, learning a second language, learning how to perform a violin concerto. All of these things have a critical period in the brain. It doesn't mean you can't learn it at a different age, but the brain is more susceptible to adapting to this new task at specific ages.
There was a time, not too many years ago, when most scientists believed that the ability to physically remodel our brains was limited to the critical period in the earliest years of childhood. Now we know it's not true. We learn all across a lifetime. But from the end of the critical period to the end of life, the brain controls its self-development, its plasticity. During this time, the brain establishes machinery that is specialized to fit into its environment. And most importantly, it can change this machinery. It is capable of rapidly revising it to accomplish this crucial initial specialization.
When I was a boy, everyone knew that a child born with a deep cleft palate was in real trouble. We knew that they would never have normal language abilities. We knew that they'd be slow to learn to read. We knew that they would be cognitively impaired. But a surgeon in Europe discovered 35 years ago maybe, of that order, that if you just fix it when the baby's young enough, none of that happens. Wasn't really inherited. So how do you explain that? Well, it turns out that the cleft palate divides the top of the roof of the mouth, and it closes off 2 tubes that drain fluid from the middle ears. And these babies were hearing everything in their native language. All of their model in their native language was, in a sense, underwater. It was all muffled. So their native language wasn't English, or it wasn't German, or it wasn't Swedish. It was muffled English. It was degraded German. It was lousy, noisy Swedish. So when you provide that baby, when you provide that brain with a clear signal, English or German or Swedish in a sharp and clear form, the normal form, then the brain can organize its representation. It can plastically revise its machinery to specialize for the sounds of its native language.
But the brain, with its wondrous ability for change, can also compensate for injury well beyond childhood.
It's usually thought that the later you undergo some trauma, the less likely it is for your brain to reorganize in a significant way. But in the case of a number of people in a study who indeed lost their eyesight after the age of 14, their brain was also able to respond. Usually what happens is that the visual cortex no longer receives signals from the eyes, again, whether that's from birth or later on, and the visual cortex takes up about a third of the brain. So that's an awful lot of the brain to have nothing to do. So it seems to recognize that no signals from the usual sources are coming, and the visual cortex, therefore, gets a new gig. Typically, it becomes sensitive to sensations arriving from the fingers. It becomes able to process signals from the fingertips, from sometimes other regions of the body. It sort of turns itself into somatosensory cortex, but in other cases, it becomes auditory cortex. What we see is, just in daily experience, a lot of people have noticed that people who are blind have a more acute sense of hearing. Well, it turns out that the physical basis for that is that their visual cortex, which again is not receiving signals from the eyes, changes careers, and it begins processing sensations from the ears and helps you hear better in the world.
While the critical period is important, it is by no means the last chance we have for our brains to improve and adapt. Indeed, improvement and adaptation is a must throughout our lives for preservation of senses, skills, and memory. Learning doesn't just increase our knowledge, it physically alters our brains and our body chemistry.
The brain has a strip called the somatosensory cortex, and that takes the feelings that enter into our neurons from your fingertips, but really over, throughout the body, every place on your skin. And each region on the skin corresponds to one little spot on the somatosensory cortex. And you have a larger region devoted to the fingertips because they're very sensitive, and hardly any region of the brain is devoted to, let's say your knee, because that's not sensitive at all. Well, it turns out that if particular regions, let's say one fingertip more than another, is used more, and you can imagine circumstances where that would be true. Reading Braille, for instance, where you have to have very sensitive fingertips and where you spend hours and hours a day feeling something with your fingertips. The region of the brain that processes those sensations expands. So it had one little amount of real estate devoted to it, let's say when you entered the world, but as you placed greater demands on that region of the brain, it responded. It got larger. So when scientists scan the regions of the brain in blind people who are adept Braille readers, it turns out that those regions are much larger than in, the rest of us who do not read Braille. So that was an early indication that, again, something as simple as behavior, the way you live your life, can alter, in this case, the